most of the data, almost all of the data actually, that you're going to encounter in the real world is going to be a Gaussian distribution of data. So we can use this curve to extrapolate on from a small number of measurements what we expect to see in a population in a much larger sample. So we can use that we can use math and statistics to sort of help us out there. So the Gaussian curve can actually be several different shapes, and the mean here is the center of the curve, and the standard deviation indicates the width of the curve. So as the number of measurements, so we're going to use x bar for mean and little s for standard deviation, and here are the equations to calculate them. As the number of measurements goes to infinity, as you're more representative of a population as opposed to a small set of measurements, you have x bar that goes to mu and s that goes to sigma. So that's just some terminology that we're going to be using. A little bit more terminology. N minus 1 is the number of degrees of freedom, and you'll see that a lot going forward in your chemistry career. It's important for a lot of PChem type stuff, and definitely for statistics. S squared is variance, and S over, so that's the standard deviation squared is variance, and S, the standard deviation over the mean times 100% is the relative standard deviation, or the coefficient of variance. So we can divide this Gaussian curve up into standard deviations, and by definition, for a Gaussian curve, as opposed to any of the other distributions, we can say that 1 sigma, this area under the curve, is equal to 68.3% of the area under the curve. 2 sigma is 95.5%, and 3 sigma is 99.7%. So if someone says that, man, you're really like 2 standard deviations out, that means that you're pretty far from the mean. That's one of the things I like to say when I think people are strange. So the equation that you would use to generate this Gaussian curve is 1 over sigma pi square root of 2 pi, quantity times e to the negative x minus mu squared over 2 sigma squared. So you don't probably need to know this equation, but that's how this curve is generated. So let's talk about the standard deviation from the mean. So this sigma of a subpopulation is much less than the sigma of a population because you have fewer measurements, and so the way that those two things are related is that the sigma n, so sigma, say sigma of 5, n equaling the number of measurements, so say sigma 5 equals the sigma of the population over the square root of 5. So as n goes up, as the number of measurements go up, then your sigma n goes down. Thus, you're more confident that your measured x bar is approximately, or is likely to be more, or is more likely to be very similar to the population mean. So basically, we call this, I do this type of stuff in my research a lot, where we're calculating how many measurements we need to have in order to get this signal-to-noise data quality that we need in order to do a good analysis. And so we call it beating it to death with statistics when we set the instrument up to run overnight and say, we're just going to have to beat it to death with statistics and tromp off into the evening to go get some rest. So that means that if you want to decrease your uncertainty in your measurement by a factor of 2, 4, 10, it requires the square, basically, of the number of measurements. The number of measurements increase by a square. So if you want to decrease the uncertainty by a factor of 2, you have to increase the number of measurements by a factor of 4. And so the 1 over n square root of n is it's both a blessing and a curse. But if you want to decrease it by a factor of 10, then you're talking about 100 additional 100 times the number of measurements. So it adds up really fast.